Today, we're going to talk about counting, or combinatorics, if you want to call it that. So, what does it mean to count? Well, let's start with an example. So, let's say we have 2 dice. So, cubical dice look something like this. So let's say I have 2 dice over here. Now, let me ask you something. What's the number of possible outcomes?
36.
Okay. Now, it sounds pretty easy because by the basic counting principle, if there are m possible outcomes of event 1 and n possible outcomes of independent event 2, then that means that the total number of outcomes for 1 and 2 should be m times n. But now, let me ask you a second question. Here, dice 1 has rolled a 2, but here, dice 2 has rolled a 4. So that's what happened on the first roll. Then, on the second roll, dice 1 rolls 4, meanwhile dice 2 rolls 2. Now, the question I want to ask you is, would you regard these two as the same outcome? Do you see a difference? I mean, here 1 is 2 and 1 is 4. Here 1 is 4 and 1 is 2. So what's the difference? I mean, if you were gambling, there would be no tangible difference between these two rolls. So that means that sometimes we don't care about the mn number. In this case, there were 6 possible outcomes for number 1, 6 possible outcomes for number 2, which gave 36 for 1 and 2. But some of those were like the cases we just saw, where one dice rolled a 2, another dice rolled a 4, and then it counted separately. One dice rolled 4, the second dice rolled 2. So this is for permutations. A permutation is when we care about order. So for example, let's say we want to figure out, we have the numbers 1, 2, and 3, and we want to figure out how many ways you can pick 2 of them. Then permutation would look something like this. You start with 1, 1, move to 1, 2, move to 1, 3, move to 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. That's 9. And I mean, you should have expected that because you have 3 possible ones for the first and 3 possible ones for the second. Meanwhile, combinations would look like this. 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. As you can see, 1, 2 has a duplicate, so we erase that duplicate, and 2, 3 has another duplicate, so we erase that, and 1, 3 has a duplicate, so we erase these 3, and we're left with these 6. But what's the formula here? How do we figure that out? And you might say, well, it's pretty obvious, isn't it? It's just triangular numbers. But that only works in this particular case, where you're picking n numbers from n plus 1 numbers. So, what if we're working not with, let's go back to 2 dice, actually. So, let's say we only care about the combinations, where we erase duplicates that just have the order swapped. Then, how many do we get? Well, you might say at first, well, we double counted every one, so it just should be 36 divided by 2 is 18, right? Wrong, because there are some outcomes, like snake eyes, that are not double counted. 1, 1 and 1, 1 are not counted as two unique permutations the same way 2, 4 and 4, 2 are. In fact, there are 6 possible rows that cannot be double counted. So we break 36 up into 30 double counted and 6, which were already counted. So then we have them because we cut out all the unnecessary ones, which were exactly half of the total, which gives us 15. And then we add that back to the 6 to get 21 total combinations. See if you can write them all down. So once again, we're hit with a pretty mysterious number. Well, in this case, it's technically not mysterious because it's the 6th triangular number. But what are you going to say when we add a third dice or a fourth? Or we change them so they're not even dice anymore. They're, for example, icosahedrons, d20s. Forgotten how to draw those, so take that. In those cases, how do we find the number of possible combinations? Well, we're going to have to generalize this. So to start, well, this isn't starting anymore. We've already finished the first part. So now, let's talk about the generalized counting principle. What happens when we have more than one die? Well, here's the thing. There can only be n dice in total. And so, let's say I roll 4 dice and out comes, I don't have enough effort in me to draw the dots anymore, out comes a 2, a 4, a 5, and a 4. Now, a 2 came up once, a 4 came up twice, and a 5 came up once, and all the other ones came up 0 times. So, we say that the number of times, if you count the number of times each one came up and sum them up, you'll just get the number of dice. Because, if there was another one, that wouldn't be a die. Same. Okay. Well, they add up to the total number of dice because the dice are the ones that give you that output. You're simply counting the total number of outputs if you're counting the individual number of times you got an output and sum them all together. So let's call n1 the number of times you got a 1, n2 the number of times you got a 2, and so on and so forth until n6. We're now trying to solve for solutions to this equation given all of these ni are greater than or equal to 0, because you can't roll something a negative number of times. So how do we solve this? Well, using the balls and urns, sometimes known as the stars and bars combinatorial method, which is one of the most important combinatorial methods. Here, we can maybe call it the dice and dividers. What does that mean? Well, we're going to start by taking 5 dividers. So, one of them is going to be labeled 2. One of them is going to be labeled 3. And so on and so forth. This one's 4. this one's 5, and this one's 6 until you hit 6. Then we roll the dice. And let's say we get that 2, 4, 5, 4 roll from before. So then we put nothing in this section. In this section, we put the die that rolled a 2. We put nothing in this section. In this section, we put the die that rolled a 4. And the other die that rolled a 4. And then in this section, we put the die that rolled a 5. And in this section, we put nothing. Great. So we're just looking for how many possible ways we can distribute these n dice, in this case 4, across these 5 dividers. So if you couldn't tell, anything to the left of the divider labeled n rolled n minus 1, while anything to the right rolled n or higher. So how do we calculate the number of ways we can arrange these? Well, first, we start by treating all of them as totally distinct. So we differentiate the 2 divider from the 3 divider from the 5 divider, and we treat this die as totally different from that die. And remember, this is temporary because this is supposed to be a combination. If this die rolled a 2 and this die rolled a 4, this should still be the exact same as this die rolling a 4 and this die rolling a 2. Okay. So now, how many ways can we arrange these? Well, that's the age-old problem of how many ways can I arrange n distinct objects. So you make a list. You start with number 1, then number 2, then number 3, all the way to number n. So for first place, you have n possible choices to pick. Then for the second place, you have to pick anything but first place. So you have n minus 1 choices, and so on and so forth. Until, for this last one, you have 1 choice left for your ranking. So the total number of ways you can make a list like this is n minus 1, n minus 2, ... 1. So this is abbreviated as n factorial. So now, how many objects do we have to distribute? Well, we have 5 dividers and n dice. So the answer should just be 5 plus n factorial, right? But remember, we're supposed to treat these dividers as totally indistinguishable, because the truth is they are, and we're supposed to treat these dice as indistinguishable, because otherwise we'd be counting permutations. This die counting 2 and this die counting 4 should be the exact same as if this die counted 2 and this die counted 4. So you divide that by the number of possible ways you could arrange the dice. That's n factorial. And the number of ways you could arrange these dividers, 5 factorial. And in fact, there are 6 minus 1 equals 5 dividers separating all our dice with results. Now, if our dice suddenly turned into d20s, then we'd be using 19 dividers instead. Really, if there were k possible outcomes to an event, and events that are occurring, then the formula is just n plus k minus 1 factorial over n factorial k minus 1 factorial. And this is abbreviated as n plus k minus 1 choose n, or k minus 1, whatever you say. So this is how we count combinations. So if we test it on that, I have to pick two numbers out of this 1, 2, 3 set from earlier. This would give us 6, right? Because we found 6 unique pairs. So how do we apply it to this situation? Well, there were 2 events. So there were 2 events occurring because the first event is you picking number 1, and the second event is you picking the second number. Then, how many possible choices do you have? Well, 3. So that means the answer is just n plus k minus 1 divided, choose k minus 1. And what's 4 choose 2? Well, it's 4 factorial over 2 factorial times 4 minus 2 factorial. Oh, crud. Try evaluating this yourself, but it gives you 24 over 2 multiplied by 2, which is equal to 24 over 4, which is 6. The exact same number that we got earlier by manually counting. And say we suddenly amp the numbers up to, instead of choosing 3, we were choosing from a list of 10. Now, I mean, it's only 10. It can't be that bad, right? So you write it out. It's 12 factorial divided by 10 factorial times 12 minus 10 factorial. What does that give you? Well, a handy note is that n factorial over k factorial is just going to be n times n minus 1 times dot 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 n minus k plus 1. So in this case, it's just 12 times 11 over 2, which is equal to 66. Yikes. That's a lot different from the 6 we saw earlier. But it's still not that big. Now let's say we maybe reduce the count to 6, but now you had to pick 3 out of every one. What do you get then? Well, n plus k minus 1, what is it? You have 3 events, and you have 6 choices. 3 plus 6 minus 1 is 8. K minus 1, well, k is 6, so that gives us 5. And 5 factorial, 3 factorial is what? Well, you get 8 times 7 times 6 over 6, which is 56. Almost the number of choices we got on the other one. And what if we had to choose 4 instead? Well, that would give us 9 divided by 4, 4. And how much would that, oh, no. Oh, yeah. And how much would this, no. Oh, yeah, it would be 5 factorial, 4 factorial. I'm stupid. So that gives us 9 times 8 times 7 times 6 divided by 4 times 3 times 2. And you get 9 times 7 times 2, which is an enormous oh crap, it's not even that enormous, it's 126. But still, there are 6 numbers here and we had to choose 4, and that's almost twice as big as when we had 10 numbers and we still had to choose 2. So, as you can see, it's really dependent on what you're messing around with here. And so, finally, the moral of the story is that if you're working with combinations, you want to reduce it to something like this. Now, tomorrow, I mean, it's fun to count, but we have to actually formalize what probability means next time. We just did combinatorics, but now we have to start defining probability. And just as a sneak peek, probability is going to be like a measure from measure theory. It takes in a set and it gives you a percentage, a probability. And we can form it based on, that's not how they look. These things called the Kolmogorov axioms. And so those are what we're going to review next time. Thank you everybody for watching.